Get ready, because we are about to launch into literally one of the most fascinating scientific detective stories ever told. We're unpacking a massive cosmic cold case regarding our closest celestial neighbor. I mean, you see it almost every single night, hanging right over our heads, right? Yet for the longest time, its very existence was a complete scientific puzzle. Today, we're going to look at the hard evidence, cross off the usual suspects, and uncover the violent, mind-blowing truth about how our little corner of the solar system actually came to be.
It's a deceptively simple question. Where did the moon come from? For thousands of years, humanity has looked up at the night sky, tracked its phases, wrote poetry about it, and used it to navigate the oceans, all without having a clue about its true origin. Was it just always there? Was it captured from the dark void of space? Did it somehow, split off from the Earth? To figure this out, we literally have to treat the solar system like a massive crime scene and look at the actual physics left behind. Okay, let's dive into this. This magnificent, cratered rock is the scene of our cosmic event. To figure out how it got there, we can't just rely on guesses. We have to look at the strict physical and chemical constraints that the universe has handed us. And right out of the gate as we start our investigation, we hit a glaring anomaly that tells us something incredibly strange happened here billions of years ago. Section 1. Our unusually large moon. So our moon is a total eccentric outlier in the solar system. I literally cannot overstate how weird the Earth-Moon system is compared to our planetary neighbors. It's the central anomaly of our whole cosmic detective story, and it's the very first clue that something highly unusual and highly specific took place in our orbital backyard. Take Jupiter, for example. It's a massive gas giant, and yeah, it has moons that are physically larger than ours. But compared to the sheer size of Jupiter itself, those moons are just tiny specks. Most moons in our solar system have a mass ratio of less than 1 to 4,000 compared to their parent planet. Now look at the Earth and our moon. Our moon has a mass ratio to Earth of about 1 to 80. I mean, that is wildly disproportionate. Aside from Pluto and Charon, this is entirely unique. So why do we have such a massive companion, proportionally speaking?
Section 2. Reading the lunar clues.
To figure this out, we need to open our detective's notepad and gather the physical evidence. We're pulling from decades of orbital data and actual rocks brought back by the Apollo missions. Let's run through these constraints real quick. First, the moon is about 50 million years younger than the rest of the solar system. Second, it is completely bone dry. It basically lacks volatile elements like water. But numbers 3 and 4? Those are our smoking guns. The moon has a bizarre lack of iron. Its density tells us it has only about a quarter of the cosmic abundance of iron compared to what we'd expect, which is way less than Earth. Yet, look at point 4, the oxygen isotopes, specifically oxygen-17 and oxygen-18. They are completely identical to Earth's. Now, isotopes vary depending on where you are in the solar system, so identical isotopes mean the Earth and Moon had to have formed from the exact same batch of materials. So here's the riddle. How can they be from the exact same material, but the Moon is missing all its iron?
On top of that, orbital physics gives us another crucial clue. Thanks to tidal forces, the moon is currently being pushed away from the Earth at a rate of 38 millimeters per year. If we rewind the clock, that means the moon used to be much, much closer, and the Earth was spinning much faster. But there's a hard limit here. If the moon started out too close to the Earth, the tidal energy loss, which shows up as extreme heat, would have literally melted the entire planet. So whatever origin theory we go with, it has to place the moon close initially, but not too close.
Section 3. The failed origin theories.
All right, now that we have our constraints, high mass, high angular momentum, no iron, identical isotopes, and a specific starting distance, we're going to cross the usual suspects right off our list. First up is the co-accretion hypothesis. The idea here is pretty simple. As the Earth was pulling itself together from the solar nebula, a smaller disk of material formed around it, and the moon accreted right alongside the Earth. Sounds perfectly logical, right? Well, we have to brutally dismiss it. Why? Because it completely fails to explain the Earth-Moon system's unusually high angular momentum. And worse, if they formed from the exact same cloud of material at the exact same time, their chemical composition should be basically identical. The moon should have a huge iron core just like Earth does, but it doesn't. So, co-accretion is crossed off the list.
Next on the chopping block, the fission hypothesis. This theory proposes that the early Earth was spinning incredibly fast, like so fast that it bulged at the equator and physically flung a giant blob of magma out into space, which then became the moon. It's a highly dramatic idea, honestly kind of cool, but we have to cross this one off too. The physics just make this dynamically implausible. Basically, the viscosity within the Earth would heavily damp the kind of resonant motion you'd need to trigger a massive fission event like that. The math just doesn't work out.
So what about the capture hypothesis? Maybe the moon formed completely independently in some other part of the solar system, wandered too close, and just got trapped by Earth's gravity. I mean, it happens with smaller asteroids around other planets, right? Well, capturing a body this massively large is incredibly difficult. It usually requires a third massive body to pass by at the exact right moment to bleed off the orbital energy. But the real nail in the coffin? Those identical oxygen isotopes. If the moon formed somewhere else in the solar system, its isotopic signature would look completely different from Earth's. So we're left with no choice but to cross-capture off too.
Section 4. The Giant Impact Hypothesis.
So, where does that leave us? Co-accretion, fission, and capture are all complete dead ends. We need a theory that explains a massive, dry, iron-poor moon with an Earth-identical isotopic signature sitting in a high angular momentum orbit. Well, it's time to reveal the true culprit, the giant impact hypothesis. Now, what's really interesting about this is that the sheer scale of the violence here is absolutely staggering. About 50 million years after the solar system started forming, the Earth was sitting at about 90% of its current mass. And sharing its orbital neighborhood was a rogue, Mars-sized planetary embryo that we now call Theia. Basically, Theia smashed into the early Earth in a cataclysmic, glancing blow. Because the Earth had already differentiated, meaning its heavy iron had already sunk to its core, Theia's impact completely obliterated itself and stripped away the Earth's outer iron-poor rock mantle, blasting it into a massive disk of debris around the Earth.
So after this incredibly violent impact strips the Earth's mantle into a superheated disk, complex fluid dynamics take over. Gravitational torques push the debris particles outward, beyond something called the Roche limit. That's basically the invisible boundary where Earth's tidal forces are no longer strong enough to tear a solid body apart. Once they're out there in the safe zone, these particles begin to clump together into moonlets. Those moonlets coalesce into a lunar seed, which rapidly sweeps up all the remaining debris. It's an incredibly elegant solution. It perfectly explains the lack of iron because the debris was just Earth's rocky outer mantle. And it explains the high angular momentum, which was added by the sheer force of the impact.
But here is the fact that absolutely blows my mind every single time I read it. We normally think of geological processes taking millions or even billions of years, right? I mean, Earth has a 4.5 billion year history. But according to smoothed particle hydrodynamic simulations, say that 3 times fast, once that massive collision happened and the debris disk was formed, the moon coalesced into a solid spherical body in just about 1 single month. 1 month! Literally in the blink of a cosmic eye, our night sky was changed forever.
Section 5. An Unsolved Cosmic Mystery.
Now, you might be thinking the case is totally closed, but science is an ongoing pursuit. The giant impact theory is by far our best model, but any good detective will tell you there are always a few lingering threads. The biggest unsolved puzzle right now is this: how exactly did the isotopes perfectly homogenize? Think about it. If the moon is largely made out of the pulverized remains of the impactor, Theia, why are its oxygen isotopes exactly identical to Earth's? Theia should have had its own unique, distinct signature. The current leading explanation is that the massive heat of the impact created a shared disk atmosphere, allowing the isotopes of the Earth and the protolunar disk to essentially mix and balance out through complex diffusion before the moon cooled down. But I'll be honest, the math on this diffusion process is super tricky, and it remains a heavily researched, active mystery today.
I want to leave you with this final provocative thought. Planetary collision models suggest that getting a glancing blow with the exact mass ratio and angle required to strip the mantle without destroying the planet entirely might only have about a 1% chance of happening. It is a highly improbable cosmic roll of the dice. Yet, having this unusually large moon stabilizes Earth's axial tilt, which regulates our climate and dictates our ocean tides, factors that are heavily linked to the evolution of complex life. This kind of invokes the anthropic principle, Perhaps the only reason we are here to even observe the moon is that this incredibly lucky 1% chance collision was absolutely necessary for us to exist in the first place. So, next time you look up at the night sky, think about that. Thank you so much for joining me for this explainer, and keep your curiosity alive.